In Elimination Addition, the scenario is very similar to a nucleophilic aromatic substitution. In fact, this is sort of an example of nucleophilic aromatic substitution where you just have to force things by just brute temperature, just the violence of high heat. The scenario is similar because we have our electrons in our benzene ring that are still going to repel any incoming nucleophile, but we are going to force it to react with a nucleophile anyway. So here you have a metal and a nonmetal. Sodium is a metal, so it has very low electronegativity, gives its electrons away to whatever it's bonded to, in this case the oxygen, and oxygen is really electronegative, so they don't share the electrons at all, and you have an ionic compound. Anytime you have a metal and a nonmetal, you have an ionic compound. Sodium has very low electronegativity. Remember that electronegativity increases as you go up and to the right on the periodic table, and sodium is way at the left. So it has low electronegativity, which means it doesn't attract, the nucleus doesn't attract the valence electrons around it very much. And because of that, sodium is huge. You'd have a sodium atom, it doesn't attract the valence electrons, so the valence electrons stay far away. And so the positive charge of sodium is spread out over an enormous space. It's diluted in space. That makes the Na plus extremely stable and makes it not interfere with our reaction at all. So I wrote it here just so that you could see that what we're really going to be interested in is the oxygen. This sodium is so big that it essentially may as well not be there. Oxygen, on the other hand, is very electronegative, which means it's small, and so if you have a full negative charge there, it's very concentrated. The electrons are really repelling each other. That's going to be much more reactive. So that's our nucleophile. We have full negative charge, and we have lone pairs. So we can recognize this hydroxide as our nucleophile. When you look at the high temperature, what you should be thinking, what you should be imagining is, oh my gosh, this hydroxide is going to move around chaotically, really, really violently, really, really fast, and when it slaps into this molecule, it's going to slap into it with a lot of force. As we mentioned in the video for nucleophilic aromatic substitution, benzene has these pi bonds, and so benzene is really another nucleophile, and the electrons in benzene will repel the electrons on this hydroxide, like charges repel. And in this case, we don't have a nitro group helping to pull the electrons away. We saw that if you have that, it helps to drain the electrons from the aromatic ring, and it makes it easier for the nucleophile to attack. In this case, we don't have that, so we have to really crank up the heat, start making this hydroxide act like a madman so that it'll rush in and overcome the repulsion of these electrons. And so that's how this mechanism gets started. So let me draw this benzene ring. And even with that high temperature, as this is moving around and getting really violent, there are just too many electrons here. There are the electrons from the benzene ring, and there are electrons from the leaving group. Bromine is pretty electronegative itself, so it pulls electrons to itself, becomes slightly negative. And it's huge. Bromine is about the size of a propane molecule. So imagine all 3 of those carbons, all 8 of those hydrogens is around the same size as a single bromine atom. So bromine is huge. It has a lot of electrons. The ring has a lot of electrons. Even at a really high temperature, this nucleophile doesn't stand a chance. How can it reach this carbon here to kick the leaving group off? How can it attack and do nucleophilic attack? Well, it kind of can't. And so it does the next best thing. It steals something that's exposed. And that is hydrogen. Hydrogen is the simplest atom on the periodic table. It's just a proton with an electron going around it. And so it can only form one bond, and that means it's always on the outside of molecules. So hydrogen is really exposed, and as this gets more and more violent, it rips a hydrogen off. It says, okay, I can't attack the carbon that has the leaving group on it. I'll attack anything. What's available? A hydrogen's available. And so the first step in this mechanism is proton transfer. Remember, proton transfer is where you move an H plus from one molecule to another. It changes the stability of molecules. Now, hydrogen can only form one bond. So if it's going to form a new bond to this oxygen, the bond it has to break. Those electrons go to form a new lone pair on that carbon. And that's the first step here. So we have this benzene ring, we have our leaving group, and now we have this very, very unstable lone pair, this negative charge that's being held really tightly close to the negative charge of the ring and the negative charge of the leaving group. And it's the repulsion of all of those electrons, the electrons of the lone pair, the electrons of the ring, the electrons in the leaving group, that pushes the leaving group off the molecule. So this lone pair goes toward the leaving group and kicks that leaving group off. So that's going to be loss of a leaving group. So in terms of storytelling, proton transfers change the stability of molecules. They either make molecules more stable or more unstable. And so you usually have them at the beginning and ends of reactions as a sort of like gas pedal and brake pedal. And loss of a leaving group subtracts stuff. It takes stuff off of a molecule. So in this case, it subtracts the leaving group bromine. Let me get some more room here. Okay. So after this step, after this loss of a leaving group, you have a really exotic intermediate. It's a benzene ring that has a triple bond in it. And this should look pretty uncomfortable. After all, these carbons on the ends of a triple bond are sp hybridized. And so they want to be 180 degrees apart. They want to have this atom and this atom 180 degrees apart, and they're clearly not doing that. So that's an extremely unstable, exotic sort of intermediate. Nonetheless, people do know that this is the mechanism because they've radio-labeled these carbons, and they've found that the nucleophile always adds to the carbon that has the leaving group on it, and it also can add to the one right next door. And that's how, and it's because of this benzyne intermediate that it does that. So at this point, the nucleophile can attack. We've at least calmed things down a little bit, improved the scenario a little bit from the beginning. If you remember in the beginning of this reaction, you had the electrons from the ring that are going to repel these incoming electrons, and you have the electrons from the leaving group. Well, now we've at least expelled the leaving group. So it's just the ring that's repelling this. But this wants to crumble apart anyway, because it has a really unstable benzyne intermediate. And benzyne, by the way, is spelled P-E-N-Z-Y-N-E. So this is so unstable already. Plus, there's a little less crowding with electrons going on because the leaving group is already left, that the nucleophile can now attack. And it could attack either of these carbons, which is why people observe when they radio label those carbons that the oxygen is sometimes on the same carbon that the leaving group was on, and sometimes it was just next door. You could draw it either way in your mechanism. Just make sure that the nucleophile attacks one of the carbons in the triple bond. One of those pi bonds breaks, the electrons go next door to form a new lone pair. So this is nucleophilic attack, and in terms of storytelling, what that's doing is it's adding. It adds something onto a molecule. So at this point, we have our aromatic ring, we have the OH on it, but next door we have a lone pair with a full negative charge, which is clearly very unstable. So how do you change the stability of things? Well, the same way we started this reaction, you change stability with a proton transfer. And like I said, you'll often see these proton transfers at the beginning and at the ends of mechanisms, because they're like a sort of gas pedal and brake pedal that makes molecules either more reactive or less reactive. So we're going to do a proton transfer to stabilize this. Hit the brakes. So we'll change the stability of this. And really, we could use water or we could use hydronium. That's the purpose of this second step here. So either one will work. You could use water or you could use hydronium. I'm going to use hydronium. And the electrons will steal one of those H pluses. Hydrogen can only form one bond, so if it's going to form this new bond, the electrons in the other bond have to go to the most electronegative place nearby. That's that oxygen in hydronium, as I've drawn it. And that gives you your product. So you have the hydrogen here. You can draw it in if you want. You don't have to. They're implied in the skeletal structures. You'll notice that through this process, we really just did a substitution reaction. We had a leaving group replaced or substituted by a nucleophile. So it's a substitution reaction. And so you see the two key steps of every substitution reaction, loss of a leaving group and nucleophilic attack. If you want to substitute one thing for another, you need to subtract the thing you want to get rid of and add the thing you want to replace it. And just around it, wrapped around it, is the gas pedal and the brake pedal of these proton transfers. And so this is what you do if you really want a nucleophile to add onto your benzene ring, but you don't have the nitro group. So you have to use really high temperatures. The problem with using such high temperatures is that sometimes they can destroy your molecule. These molecules are not indestructible. And when in such a violent beaker, your molecule can crumble apart. But if you just need to put an OH on a bromobenzene, for example, this reaction will serve you well, and this is the mechanism for it.